lost as well. Okay, so let's continue. Okay, so remember yesterday we were talking about how to define a hyperplane, in this case here a straight line, okay, to separate data from two classes, okay? And we have to consider that the classes are linearly separable, okay? I can separate them with a straight line. So we were saying that when I am training my perceptron,
hi, can you just remember the perceptron concept? Because
yes.
Yesterday I was really tired when you started, and then I don't really remember.
Here. This is a concept of the perceptron, okay? So you have a training instance. This is an example, okay? We call an example. It has n features. To each feature you associate a weight. So what you have here, V, is a linear combination of a vector of wages and a vector that represents your input instance, okay? And you have the bias that I inserted into the vectors, okay, as an extra input, okay? And the objective of the bias is to move the hyperplane, okay? Is it okay? So there is a training algorithm that's going to adjust these wages in order to adjust the correct hyperplane, okay? During the training process, okay, every time I present an instance, I calculate the error of the perceptron. Then using this error, there is an algorithm that corrects the wages of the perceptron, okay? So the first, if you look at the first time a hyperplane is drawn, it will be a wrong hyperplane. It will not classify the instances. Then with time, this hyperplane is going to be corrected until I find the correct hyperplane, which is positioned between the patterns of each class, okay? Nice. Yeah, you can ask.
So what we are trying to find is the right weight vector to produce a hyperplane that can separate the data. Is that it?
Yes.
Okay.
That's exactly this.
Okay, thank you.
Yeah. So during training, we're going to see if we give an input instance to the perceptron, and the instance belongs to the positive class, but the perceptron gives a negative class. Then we have to correct the weights using a learning rate, as I explained yesterday. Okay? And the size of the learning rate controls the amount of updating we're going to apply to the wages. Nice? We are going to see that. The higher the higher the learning rate, faster is the learning, but we can skip the concepts of, minimum global and etc. Okay. So here, look, we are going to use a sine function that has V as argument. V is the linear combination of inputs and weights. Okay. So after getting this linear combination, we pass this linear combination into a function that returns to us +1 or -1, depending on the value of V. Good? So the output of the artificial neuron here, Y is written in a compact form, will be the linear combination used as an argument to a sine function. Okay? So we have a linear combination of inputs and outputs. The linear combination, this result number, we give as argument to a sine function that returns to us +1 or -1. That will be the class of the instance. Nice. So, in the convergence algorithm, okay, we have a desired answer because this is also supervised learning. So we have a bunch of instances, okay, and we have the desired output, +1 or -1, okay. So the desired output, we are going to say that's +1 if it belongs to a given class 1, and it's going to be -1 if it belongs to another class 2 here, okay. To adjust the weights of the perceptron, we use this formulation here, okay? The weight in a next interaction, what's the next interaction? When I'm going to give as input another instance during the training process. So the weight in the next interaction is the weight in the current interaction plus the learning rate multiplied by an error. Okay, the error is the desired output minus the predicted output, and multiplied by the sign that is being given as input to the neuron. Okay, the sign that's associated to that weight. Remember that we have a vector x. Okay, this is a vectorial form. We have a vector x. Each position of the vector x is associated to a weight. Remember that? Okay, so if you break this formulation into that summation, you are going to have an xy associated with a wy, okay? So the sign that is connected to the neuron is the xy. It's one feature of the whole instance. And this feature is associated to wy. Okay? So this is the learning rate, and this is what we call error signal. Nice. So what happens here is that we are calculating an algorithm that's called gradient descent. Okay? The objective of the gradient descent is that given an error function, okay, we calculate the derivative of the derivative of the error in the direction of each weight that we want to update. Okay, this error function here has a surface. Okay, if we calculate for each weight that we want to update, if we calculate the derivative of that error in the direction of this weight, we are going to go in the opposite direction of the gradient vector that's related to this error function. If we go to the opposite direction to the minimum of the gradient, we go to the minimum of the function. Okay, so this is what the gradient descent does. This minus here stands for the gradient descent, okay? So the concept is actually really simple. Like when I am calculating here the derivatives, if the derivative here has a positive sign, that means we need to decrease the value of w. So if I decrease the value of w, I'm going to the direction of the minimum of the error. If the derivative is negative, we have to increase the w, and we go to the direction of the minimum of the error. Okay, so for example, take here an example here. So we are going to, in the vector formulation, we are going to calculate the derivative of the error, okay, in the direction of the vector w. Okay, but we have to do this for all positions of the vector w, okay, because we are adjusting all the weights. So how do we calculate this derivative? Okay, the derivative of the error in the direction of WE, which is just one weight of the perceptron, is going to be the derivative of the error. What's the error? The desired output minus the predicted output, okay, in the direction of that W, okay? Then if we do the derivation here, what's going to remain is that only the desired output, this is a constant, okay, we can ignore it. So it's the desired output minus the predicted output. The predicted output, y, we already know how to calculate, is the linear combination, okay? The desired output, that's the linear combination, okay? So we have this, okay, times, this minus go here, the input in that signal, the signal input associated to y, okay? And then that leaves us with that initial formulation, like learning rate times error times the input signal in the neuron. Learning rate, error signal, input in the neuron. Okay? Is it okay? Good. So let's make an example to see how easy it's to use the perceptron, okay? So consider we have these two examples. We have 3 features, okay, for each example, and we have the desired classes. And this is a perceptron, our initial perceptron. These weights are all set randomly. Usually, we have a search space, okay? Consider that we have a search space of wages. We don't know what are the correct wages. So we give an initial guess, okay? So these are the initial wages that were a guess that I gave to my perceptron. Usually, we initialize the wages with small values, like between the range of -1 and +1, or minus 0.5 plus 0.5. Usually very small wages. Now, given these weights, we are going to initiate our training. Remember, we need data to train the algorithm, okay? And this is our data. Good. Now, so we have our desired class. That's why this is called the supervised learning, okay? And we have a function that says that if, okay, the desired output, okay, if the output is higher than 0, then the class is 1. If the output is less than 0, then the class is -1. Okay, this we already know. Okay, so we are going to start the first epoch. What's an epoch when I'm training a neural network? An epoch is when I pass all the instances, all my data set to the neural network. Okay? When I finishing giving all the instances as input to the neural network, I finished a epoch. So we say that we train the neural network, in this case only the perceptron, okay? We train by, I don't know, any epochs, okay? And we usually calculate the error of the network in each epoch, and we see how the error is decreasing with the training in each epoch, okay? So in the first epoch, we are going to get the first instance, okay? Remember the values of the first instance, 0, 0, 1, okay? So 0, 0, 1. And you have a fixed bias -1 here. It could be 1, okay, but in this case it's -1. Usually we use the value 1, okay? So what we do, we multiply, we calculate the linear combination. So -1 plus f0 plus, -1 times 0.5 plus 0 times 0.4 plus 0 minus 0.5 plus 1 times 0.6. And you have an output, 0.1. This output is given to the sign function, okay, that we call here activation function. So the activation function gives the output of the neural. In this case, is 1, because the sign of 0.1 is positive, okay, this is a positive number. Now we have to calculate the error of the perceptron in this instance. So we have to calculate the desired output minus the given, okay, the predicted output. So we have an error of -2. Okay, we have an error. Now we are going to get this error, -2, and use it to correct the weights of the perceptron. So W0, the new W0, the W0 in the next interaction, is going to be the current W0 plus the learning rate, which is 0.4, okay, times the error, times the signal that is associated to this weight. The signal is -1. So the resulting of this calculation is 1.3. Now the new value of 0.5 is going to be 1.3. Okay? Is it okay? And we continue the correction for all the wages. So we're going to correct now the wage W1. So the new wage is going to be the previous wage plus learning rate times error times the signal that is associated to W1, which in this case is 0. So 0 here will multiply and we'll make everything be 0 and will be no correction. Okay? Nice. And the same thing is going to happen here. So let's jump to this input here. W6. So W3, okay, the new W3 is going to be the previous one, plus a learning rate times error times the input associated to W3. So this calculation returns me the value 0.2. Okay, so minus 0.2 is going to be the new wage, the new W2 wage. So this is my vector of weights, my vector W, okay? Okay, nice. Good, now we are going to get the next instance. Okay, we are still in the first epoch. We are going to get the next instance of our data set. And we are going to do the same thing. We are going to calculate the output. The output in this case, the output with the new wages, okay, is minus 0.9. Okay, so the signal of minus 0.9 is -1. We calculate the error, desired output minus predicted output. So we have the error value equal 2. Now we have to use this error value to correct these wages. And we are going to do the same thing we did before. Okay? The same calculations. So the previous, the new W is going to be the current W plus a learning rate, plus the error, and plus the signal that's associated to that wage. So in this case, we're going to correct this wage. It's going to be 0.5. We are going to do the same with this wage. The new wage is going to be 1.2. Okay. And of course, I didn't make the calculations here because the input is 0. 0 is going to, everything is going to be 0. We will have no updating, okay? Nice. Now we are going to start the second epoch. So all the instances of my data set were given as input to the neural network, okay? We finished the first epoch. Now we're going to start the second epoch, yeah.
Sorry, could you repeat how can I set the value of learning rate?
The value of the learning rate is also initial guess. It has to be it has to be a positive number between 0, higher than 0, of course, and 1. Okay, the higher the value, the faster the learning. Usually we use a very small value like 0.01 or 0.3. That depends on the application.
I don't understand very well what is X0.
X0 is the input associated to the bias. Okay? Usually we use a fixed number, 1 or -1, just to move the hyperplane. Okay? More questions? Nice. So let's initiate the second epoch. Now, if you look at the calculations, okay, of the linear combination given as input to the function, you see that the output is -1. Now we calculate the error, -1, which is the desired output, minus the predicted output, gives me an error equal to 0. So if the error is equal to 0, I don't need to correct the weights, because this hyperplane is correctly classifying instance E1. Good? Okay, so let's go to the second instance. The same thing is going to happen, okay? So this hyperplane, okay, when receiving E1 as E2, sorry, as input, we return a value equal to 1. Okay, if we calculate the error, desired output minus predicted output, we are going to have the error 0. So we don't have to correct the weights. So this is our final neural network. Okay, here I am giving a very simple example with only 2 instances, an illustrative example, and I am training the neural network until I encounter no error. Okay? But in real world applications, what we do is that we start monitoring the error in a validation data set, for example, or in the training data set. But a good practice is to divide our training data in training and validation. Then I do this training in the training data set and monitor the validation error in the validation data set for each epoch. Okay? And there should be a tendency of the error in the validation data set decrease together with the error in the training data set. If in one time, for a given epoch, from a given epoch onwards, the error in the validation data set starts to increase and the error in the training continues decreasing, then we have an overfitting. We have to stop training, because there's a tendency that my neural networks memorizing the training data and starts to committing mistakes in the validation data. Then we have to stop the training at that point to avoid overfitting.
I guess you mentioned last time that there's a theorem that the error should go to the global minimum, right?
Yeah, but in this case, in this simple case, I'm
for
talking
this
about
single
yes.
layer. Okay, you're talking about a more
we are
complicated
going,
architecture.
Yes, we are going to work, for example, with the multi-layer perceptron. So what we are going to do is to monitor a training error, and let me get another color, and a validation error. Okay, so there should be a tendency of the validation error to decrease together with the training error. But if at some point the validation error starts increasing and the training errors continue decreasing, then at this point we say that we are getting an overfitting. Okay, because our neural networks is starting memorizing training data and the validation and it's not getting correct predictions in the validation data. So we should stop training here. Okay. More questions? Okay, now let's apply our perceptron, okay, to make predictions in new instances. So it is easy, right? We just get the values of the features and calculate the linear combination, gets this linear combination and use it to give as input a activation function that gives us the sign, okay? So we are going to get here the classes, and we are going to see that the class, for instance, E1 is going to be 1. That's the prediction, okay? For instance 2 is going to be 1 as well. For instance 3 is going to be -1. Just making the linear combinations given as input to the sign function. Good? That's the prediction. Any questions?
Could you just change a little bit to the board because of the people at home?
I'll change back to the board.
Because you use the board and they can't see the plot that you did on the about the
Ah,
error.
okay. Nice. Okay. And one interesting thing is that another concept is the concept of hypothesis, okay? So we are, remember, we are inducing our Perceptron because we want to find a hyperplane, okay, that divides these two training data, okay? And we have to consider that the training data is linearly separable, okay? So when I start training, the first hyperplanes will be wrong ones, okay? So we call this a hypothesis. So every time we are training a machine learning model and we find, and we tune a given hyperparameter in a given interaction, the resulting model is a hypothesis. So the first hypotheses are terrible ones, are wrong hypotheses, okay, bad hypotheses. As the training goes on, we start getting better hypothesis until at the end we get a final hypothesis that's going to be our model, our final hyperplane that separates data, okay? This is an important concept that you should know. It is valid for every machine learning algorithm, okay? Nice. So let's make some implementation of the Perceptron. Do you have the code I sent to Guy this morning? I think she sent to you. Okay. So, because the Perceptron is very, very easy, we are going to do the implementation by hand, okay? We're not going to use any package because it's very easy. And then you can know how the fundamental artificial neuron works. Okay, that's going to be good. So let's go. Here. Okay, we are going to use some illustrative data here, okay? Just for you to know how the things work, a very illustrative and easy data. So what I'm going to use here is the data set iris, okay? Is it okay the size of the letters for you here? Bigger, okay. Okay, so we are going to load the data iris, okay? Here. This data set is a data set that is related to okay. Should I wait? Yeah? Okay. Yeah, I'm just going to talk about the data set while we're loading the things, okay? So this is a very small data set, okay? It has 150 instances, okay? 50 instances belonging to each of the 3 classes, which are species of flowers. So we have 3 species, versicolor, setosa, and virginica. 3 species of flowers, okay? And we have 4 features for each flower, which is the sepal length, sepal width, the length of the petal, and the width of the petal. Okay, so we want to classify the species based on the features. Okay, traditional machine learning problem. Okay, so here you can see the dimensionality of the data, okay, 150 instances, 5 features, one of the 5 is a target, okay. The target is this species here. Okay, can I go on? Good. So we are going to see here how the features separate the data. Okay, with this function here, I'm going to plot the 4 features, okay, and put a color to each feature according to the class, okay. Sorry, the color to each feature, no, the color to each class according to the class, the color to each point, each instance, according to the class this instance belongs to, okay. So here, we can see here how each feature, a pairwise comparison of 2 features to see how they separate data, okay. So what we can see here, what can we see here? Do you have a, based in what we just saw, considering the abilities of the perceptron, what can you conclude? Yeah. But we have 3 classes. So?
Maybe make 2 models or 2 perceptrons.
Yep. You see that one class is linearly separable of the other 2.
Yeah.
But you have 2 classes that are not linearly separable. You cannot fit a perceptron to separate instances here.
Okay.
You can only fit a perceptron to separate this instance from this other, from this instance that belong to the other 2 classes. Okay. So with the perceptron, we are not going to be able to solve this problem. We are going only to be able to separate one class from other 2. Okay.
What would happen if we try to use a perceptron, but the classes are not linear separable? It would never reach a...
Yeah, it will run forever. I mean, if your stopping criteria, if your stopping criterion is that you must predict correctly all the instances, then it will run forever. It will never find the correct hyperplane.
I have the question if here in this dimension it's not linearly separable, but if we can increase the dimension and to see if in another higher dimension are linearly separable and still use one neuron instead of one network.
That's a very good question. We can do that. There is an algorithm. We are not going to see it, but there is an algorithm that, for example, let's say here we have again, okay? Now I'm going to erase this. Okay, now suppose that we have here, so x1, x2, okay? And we have some data, let's say, like this. And let's say we have another data which is like this. Okay, just an illustrative example. So it is impossible to draw a straight line here to separate this instance, okay? But yeah, what you can do is that you can, how can I do that? You can increase the dimension, okay, using some specific mathematical transformation. You can increase the dimension x1, x2, then x3, and now you are going to have something that I don't know how to draw. Okay, but it will be something like, I don't know. And then with this, you can draw like a hyperplane that's going to be a plane, like that separates the data. You know that a plane is passing here, you know? Okay, then with this, yeah, that will be possible to separate the data because it becomes linearly separable. Okay? Yeah. Okay, let's go back to our implementation. Continuing here. So now, okay, because we saw that we can work with only 2 features, okay, to get linearly separable instances. What we should do is that we should work with only 2 features. Okay, so what I'm doing here is that I am getting 2 features. Okay, I'm getting a data set X here. That's going to be a matrix with 2 features, okay? Sepal with it and petal with it here. Sepal with it. And where's petal with it? Petal with it. So here. Okay, we are going to work with this. Okay. So I just got here. I'm just showing part of the data set here. Nice. And one thing we should do, look at the instances, okay? One thing we should do is to scale the instances, because we are actually working here with a distance function, okay? When we are working with the perceptron, actually what's going on? We are calculating, for example, we are just moving a hyperplane close and far from the instances in the space. Okay, so actually this is like calculating the internal product between 2 vectors. Okay, and I'm moving the vectors close and away. I cannot move the vector of instances because these are my training instances and they are fixed in space. But I can move the W vector. Okay, so I'm actually calculating distances between vectors when I do these mathematical calculations. So when I work with distances, it is important that we normalize, okay, our features, because we don't want one feature to contribute more to the calculations than other feature. So we are going to scale our data here to be in mean 0 and standard deviation equals 1.
Yeah, we're doing the perceptron by hand, but in a function, would it do this, or do we have to do it before the input? Do we always have to do
we usually use another function to scale data, then we give it as input to the neural network.
Okay, so the neural network doesn't do that by itself?
Yeah, unless you have a package prepared that does that for you. Like you call the package and it pre-processes data and gives as input to the neural network. But otherwise, you have to do it by hand.
And could you give us like the packages afterwards, after we finish?
Yeah, I'm going to. There is a packaging area called neural networks. Neural, I think it's neural. We are going to use it. Then we are going to work with multi-layer perceptrons. Here I'm giving the concept of the perceptron, because then you know how the things work in the basic, you know? Of course, you are never going to use a perceptron for your practical works, okay, real world data, because it doesn't work. But the concept of the artificial neural is the same one up to today, okay, it's the same one. Okay. So here I'm scaling data. Look at the data now. Okay. And now what I'm going to do here is that I'm going to label my data set with the labels +1 and -1. Okay. Instead of working with the categorical class, I cannot work with the categorical class because the neural network only works with a numeric variables, right? So I'm just changing the values. Like if the class is setosa, I'm changing to +1 and -1 otherwise. Okay. So here I have my new labels. Is it okay?
I didn't quite get it. Why did we just use 2 variables, the sepal width and the petal width?
Because here I want to show you how to draw the straight line, And working with two variables here, I can work with a data set where the instances are linearly separable. Okay? These ones are going to be linearly separable of this here. I can draw a straight line here.
Okay, but in all others we could also draw a
Oh yeah, I
straight line.
just get I just got two variables here just to show, but I could have gotten any of two variables, any combination. Okay.
No particular reason.
Good. Yeah, here. Okay. Now let's begin our implementation, okay, by hand for you to understand. So what I'm doing here is that I am building a vector of biases. Okay. Remember that the bias is I'm having a value, an input that I'm going to associate with the bias. Okay. So this input is going to be equal to 1. Okay. So I'm building a vector of ones. What's the size of this vector? The size of my data set, the number of instances of my data set. And then I'm concatenating, okay, this bias vector as a third column of my data set. See? Okay, because remember I have the x and I'm including a 1 in the vector of each instance. The same nomenclature we use it in these slides, okay? Good. Now I'm going to concatenate the classes. See, I'm getting my instances and putting a fourth column here, the column of the classes. So here I have the column of the classes. Okay, if I continue there and see all the others, you're going to see that this is going to change to -1, okay? All the classes are here. And now I have to generate random initial wages, okay? So I'm going to generate 3 wages randomly between the values -1 and 1, okay? And here are my wages. Actually, I don't need to use head here. Here are my wages, okay? Why do I have 3 wages? Because we have 2 input features plus a bias. Okay? Good. Now we are going to implement the main Perceptron training loop. Okay? This function is going to receive the wages, the training data set, and return to me the updated wages. So you are going to see that this is very easy. So it's going to receive data, wages, and we return the trained wages. So here I'm setting a learning rate, 0.3. Okay. Here are just control variables, okay, to control the error, to control the number of epochs I'm training the Perceptron. Okay. And I'm going to train my Perceptron until I predict correctly all the instances. Okay. I'm going to train until I get the corrected predictions of every instance. So initially I have no error. Okay. I increase the epochs here because the epochs are 0, so here's the first epoch. Okay. I increase the epochs of each interaction. And here is a mean error that I'm going to calculate for each epoch. Okay. Nice. So the first thing to do is to sample our data, okay? Because it's good, okay, to sample our data in order to make our gradient descent algorithm stochastic, okay? Because if I present the data in order, like for example, all the instances of one class, then all the instances of the other class, then I will make the learning more difficult because it will set in a hyperplane just for one instance, you know, just for one class, then it's going to start viewing the instance of other classes. I mean, then it's going to start to see all instances from just one class. So it is better to make the process randomly, to adjust the hyperplanes at each interaction, okay? Yeah, so I'm sampling data, shuffling data, okay? I'm just constructing a vector here, okay, with numbers from 1 to the number of instances, and this vector will be these numbers from 1 to the number of instances randomly sorted. And then I'm indexing my data set with these numbers, shuffled numbers, okay? Nice. Now for each instance here, I'm going to start my training, okay? So the first thing I'm going to calculate is what we call the activation potential of the neuron. That's our linear combination between weights and inputs, okay? That's our V. So I'm doing it like step by step. I could calculate it using R just in one line of code, okay? Using the potential of R to multiply vectors. But I'm doing it here step by step, just for you to understand. So for J in 1 to all the weights, what I'm doing here, I am multiplying an input by a wage, okay? Input multiplied by a wage plus the next input multiplied by the next wage plus the next input to the next wage, and so on, okay? And then I have the activation potential. Now I'm going to calculate the output of the neuron. I just get the activation potential and give as argument to a function sign that returns me the sign of the number, +1 or -1. And with this, I calculate the error, okay? I am getting the error, desired output, minus prediction, and squaring it, okay? I could have just done this, okay? But I multiplied it 2 times here. The number multiplied by itself. And I summing up here in the error. So I'm accumulating the error for every instance. Okay, this is only one epoch. I'm passing, look here. This for here is going to be for one epoch. When the for terminates, then we are going to fall in this while here. It will check if the error is equal to 1. If not, then it stops, okay? Because if the error here is equal to 0, it means that I could classify all instances. Okay, nice. Getting the output of my neuron, what I'm going to do, I'm going to see if I make a correct prediction. Okay, of course I could have checked this here, because if there is no error, then I made a corrected prediction, but I'm checking here. So if the prediction is different from the real value of the output, then I committed an error, okay? If I committed an error, I have to adjust all the wages. So here I'm going to make a loop for all the wages, and I'm going to adjust the wages. So a wage, okay, is equal to itself plus, this is the delta, okay? This is the updating we're going to apply to the wage. So the updating is going to be a learning rate times the error, okay, times the signal that is associated to this wage. Okay, so remember we are in instance Y, we are getting the class of instance Y. We are verifying here if it's different from the predicted output, and we are multiplying here by the input associated to the wage J, okay? The input associated to wage J, okay, is the sign J, okay, the feature J of my input instance. Is it okay? Okay, with this for loop, I update the wages, and that's it. I do this here, look, for all the instances. This is this for loop for all the instances. Once I finish passing all the instances, I finished an epoch. Now an epoch is finished. Now I'm going to calculate the mean error. I just get the error in the epoch, the accumulated error for all the instances, and I divide by the number of instances in my data set. Okay, and I have a mean error. And I'm here just printing the mean error. Okay. If I don't commit any mistakes, then this error, this variable error key will never be assigned the value 1. And then it's going to be 0. When this happens, the program is going to get out of this loop while here. And then we finish with any epochs. Okay? And then I return the wage trained. So if we execute this, it's actually going to be very fast. Oh, sorry, this is just a function, okay? I just loaded the function. Okay. Now here I'm going to call the training function, okay? I'm going to call Perceptron train, passing the data set and the wages I randomly initiated. Then it trained it very fast, as you can see. Every time you execute, it's going to be different, okay? The hyperplane is going to be a little bit different because the wages were randomly initiated differently, okay? The instances were passed to the network differently because I random them, I shuffle them every time in each epoch, okay? So every time we execute, we will get a little bit different hyperplane. That's normal. So now here, it finished with 3 epochs. Now we are going to compare the wages, the old wages, with the wages we just trained here. So you are going to see, there's a spoiler here. See, that's different. These were our initial wages, and these are our new wages. Okay? Now what we are going to do here is we are going to plot data, and we are going to plot the hyperplane we obtained, okay? So what I'm doing here is that I'm plotting data, and I'm plotting the points, okay, here. Let's do this here to make it separable. Oh no. Why not? Plot, print.
I think it's the margins again.
Hmm? Oh no, come on. Yeah, see? So these are my data. So we have to find a straight line here that separates this data, okay? Nice. So we are going to construct the hyperplane, okay? We know here, okay, that the equation here in the form y equals mx plus k is the reduction equation of the line, okay? You know that. So m is the slope, okay? And k, we know that's the ordinate where the line crosses the y-axis, okay? The intercept. The same thing we did with linear regression. Remember, we have beta 0 and beta 1. We have the same thing now for the reduction equation of the line. Okay, we have a beta 0 and beta 1, the slope and the intercept. Okay, so this reduced equation, we can obtain it directly using the general equation, which is ax plus by plus c equals 0. Okay, see that this a, b, and c are the wages we just found. Okay, because we have a variable x1, a variable x2, and a bias plus 1, fixed number, +1. Okay, so using these values, we can calculate n and key. So we are going to calculate using we are going to obtain n, okay, and key, slope and intercept, using the values of our wages. Great. And then we are going to draw a straight line using the intercept and the slope associated to our obtained using our wages, okay? So let's do it. And here is our, I should have it drawn here. Where is it? Oh, here it is. Okay, this is our straight line. If we run our Perceptron again, we can probably obtain a different hyperplane. I'm going to initialize the wages again. Here. Okay, different wages. And I'm going to run the Perceptron again. Okay, and I am going to plot again our hyperplane. Here we have a different hyperplane, okay? Is it okay? Questions? Good. So what we are going to do now is we are going to classify new data. Okay, we are going to construct a function here that I'm calling Perceptron that
We can see by your data that it is possible to draw a lot of possible lines.
yeah.
So I was thinking maybe we can use the model to generate a spectrum of lines because this one is adequate for this trained data. So I was thinking if we can generate like a lot of lines and then use, I don't know, what average line for.
Yeah, we could do that actually, maybe. Yeah, there are some algorithms like the support vector machine that what it actually does is to get a hyperplane that maximizes the separation between the two classes. So it would be more or less like if we had a hyperplane that it's just like very, very close of this point here, another hyperplane that's very, very close of this point here, okay, a hyperplane that's very close of this data, another hyperplane that's very close of this data, and our true hyperplane, separation hyperplane, will be the one in the middle. Okay, we can do that. Okay. But running, I don't see advantage of running many perceptrons, and because you just want one hyperplane that generalizes. I don't see advantage of running many times.
Thank you.
Okay.
I had a question relating to that. I mean, if you do one perceptron and you run it, and I don't know, you just train something. If you input new data, how do you know, like, how do you quantify the error of like your algorithm?
Okay, if you have a test data set, that is already labeled, then it is easy. You just compare the predicted output with the desired one and calculate the error, okay, the accuracy, for example. Otherwise, if you have, for example, new obtained data in the lab, and you have just, you don't know the class of that, I don't know, think of any problem in your, any day problem that you work, okay? You obtain data, you want to find a function of the data, a category for the data, but you don't know. It's a new data found in the lab. Then you can use the algorithm to predict a given data with a given probability, because you can look at the output of the perceptron, for example, and see, oh, for this instance here, the output was 0.95. Okay, for example, was very high. And then, yeah, you can say, oh, there's a high probability of this guy here, this instance belongs to this positive class. But you have to check that in the lab. There's no way of seeing if the algorithm is correctly classifying the instances. Good. So what we are going to do here is now is to classify new data, as I was saying. So we are going to make a function here that receives as arguments an instance and the wages. Of course, the trained wages, okay? And I'm going to make a loop here that computes the linear combination of attributes plus wages, okay? And gives this linear combination to as input to a sine function and return the output of the neuron. Good. Now I'm going to create some data set, some test instance here. If we look at our hyperplane, oh no, let's say we can have a point here, maybe 2, and I don't know, 0.5, 2, or I don't know, -1 and 0.5, you know what I mean, right? I get a point here in this two-dimensional space, okay? That's why I'm doing here. I'm passing a point here together with a value for a bias that we use it to train the neural network, okay? So I'm passing here 2.5, for example, and 1. 2.5 and 1. So the expected output should be -1. Okay? If you see here, -1. If I get a point 1 minus 1, 1 minus 1, it will be a positive point here in this region. Okay? So as you can see here, 1. Okay? Nice. So let's make things more funny. Oh, this here is wrong. So let's work with the multi-layer perceptron. Yeah. Okay. Now we are going to work with problems, okay, that are not linearly separable.
Sorry, I have a question related. When is recommendable to use the decision trees instead of Perceptron?
Yeah, the perceptor you're going never to use, okay, because the perceptron doesn't work for real-world problems. Okay, very simple problems it cannot solve.
Yeah.
But when to use a neural network, that's what we're going to see now, a multi-layer perceptron and a decision tree. That really, again, depends on what you want and depends on your data. So, for example, if you have categorical data and you have to perform, like, you want to perform a feature selection and you want an interpretable model, you want a model that gives you an explanation why it is predicting a given value, then it is better to use a decision tree, okay? If you are more interested in a more robust, for example, a more robust model that has an ability to better classify a given type of data more accurately, for example, images. Usually with images we use neural networks because they are more, they can extract more features from data and combine these features and give you a more accurate prediction. But you are not interested in explanation. Then it's better to go for a neural network. So you really have to ponder what to do. There's no direct answer for that. Good. So, before going to the multi-layer perceptron, as I was saying, we know that the perceptron can only classify linearly separable data, right? Now think about the XOR problem. Do you remember the XOR problem? The XOR function. Yeah, if you have, let's say, what's the value for XOR? 1, right? 1. Is it right? Yeah, I think so. So if you get this data and plot here in a two-dimensional space, what you're going to have a point here, right? You're going to have another point here. And then you are going to have a point here. And another point here. Yeah, it really doesn't matter for our explanation, okay? But look, if you have these points, is it possible to separate these points with a hyperplane? Only one straight line? So see, it's a very, very easy problem, very easy, only 4 points, and you cannot solve it with a perceptron.
Isn't the table for exclusive OR the opposite of this?
Yeah, but it really doesn't matter.
It ends up being the same. Just for
it really doesn't matter.
Yeah.
Yeah, it's only for you to see that it is impossible to draw a straight line, okay, to separate 2 points from the other 2 points. Okay, so I mean, because of this, the studies on neural networks stopped for some years. Okay, until the guys tried again to find another algorithm. Okay, that is the backpropagation that we're going to see now. Okay, to train a multi-layer perceptron that could solve this kind of problems that are not linearly separable. Okay, so we are going to see this now. No, it's another button. Yeah. Okay. Nice. So the multi-layer perceptron was constructed to overcome the perceptron practical limitations. Okay, I just gave you an example of a practical limitation. Okay. So now the model of each neuron includes a nonlinear and differentiable activation function. Okay, so we have a function now where we can compute the derivative of that function. Okay, and it has to be a nonlinear function. It has to apply a nonlinear transformation in that linear combination. Okay, it's going to contain one or more hidden layers between the input and output. Okay, and has a high degree of connectivity. All the neurons are connected to all other neurons. Okay, have in mind that we have many different types of neural networks here. Okay, I'm going to present you just one of them, but we have recurrent neural networks where neurons have as input the outputs of themselves, you know. Yeah, we have convolutional neural networks. We have neural networks for clustering. We have a lot of variations for neural networks. But I'm going to present you here for classification. So, how do we learn this kind of neural networks? With backpropagation. Okay? This really has useful applications. You can apply it in your data, in your real-world data. Okay? So the backpropagation algorithm has a forward phase. Okay, where we have the weights fixed, and we just compute the sign, the output of the neural network. Okay, it's the same thing we did now for perceptron, but the output of one neuron is going to be used as input for another neuron. Okay, but it's the same kind of computation. Nice. Okay. So we don't change anything in the neural network. We just compute the outputs of the neurons. And we are going to change the activation function with a non-linearity. Okay. Now, so, and then we have the backwards phase. The backward phase, we compute an error in the output of the neural network, just like we did with Perceptron. So we have a desired output. We have the output of the neural network. We compute an error, that's desired output minus prediction. And then we are going to use this error now to correct the weights. The thing is, we have output neurons that are associated with the outputs. Then we can compute the direct error associated with that output neurons. But what about the other neurons? Okay, how can we compute the errors associated with these neurons? So we need a new algorithm that does that for us. Okay, because we are going to adjust these weights based on the error that was computed there in the output layer. Okay? So the idea is that the error is going to be propagated backwards to the layers. Okay, and we are going to do some mathematical calculations to see how we are going to use that signal there to adjust the weights of the previous layers. Nice. So this is a simple illustration of a multi-layer perceptron. So each of these here is an artificial neuron. Okay, and it is a McCulloch and Pitts neuron. It's the same neuron we saw in the perceptron. It's the same formulation. You have inputs, and to each input you have an associated weight. Okay, the only difference is that we are going to, instead of using the sign function as the activation function, we are going to use a non-linear function. And the function we can calculate the derivative. Nice? So we are going to pass an input instance here, calculate the output here, compute an error, because we have the desired output, and use this error to adjust all the weights. Okay. Okay, so we can say that we have signal functions and error functions. Signals, né? Signal error signals and function signals. Okay, so signals that go forward and signals that go backwards. Okay. Here is an interesting thing. What's the function of the hidden neurons? What do we have hidden neurons? Okay, because they act as attribute detectors. Okay, as the learning process goes on, these neurons begin to discover attributes in data. Okay, think about the classification of images. I guess many of you have heard about convolutional neural networks. Okay, so think about images. I think it's the easiest illustration I can give. So the first neurons are going to extract simple features like a corner, okay, a difference between two colors, okay, a border, things like that. The other layers, the other neurons, the neurons in the next layer, are going to combine these features to find more complex objects. The other layers are going to combine these to find more complex objects. That's why you can detect an eye, okay, detect a mouth, because you combine characteristics that you learned in the layers. Okay, giving another example. Suppose you have like this kind of data here. Okay, well, this is linear separable. Okay, but this one here. Let me just change. Okay. Yeah, now suppose you have this kind of data. So what's going to happen is that the first neurons in the first layer are going to draw like straight lines. That's what's going to happen. And then these straight lines are going to be combined, okay? Like straight, I mean, suppose here. The first layer, the neurons of the first layer, draw straight lines. You see straight lines. The neurons of the second layer are going to combine these lines, okay, and construct like more complex hyperplane separations, and they're going to separate the data. You know, that's what's going to happen. I will give you an illustrative example. Okay, so the first layer, for example, can draw straight lines in the decision space. The second layer combines these lines, forming convex regions. The third layer combines convex figures, producing more abstract shapes in order to separate data. I'm going to give you an illustration here, considering a space of 2 dimensions only, okay, in order for you to visualize. So see, the first layer draw, for example, these straight lines here. Okay, the second layer combines these lines and makes 2 regions. Okay, so with this, for example, we could solve the XOR problem. Okay, we have one point here, one other point here. Okay, then you can separate the data. See? Good. If you continue, you can obtain more abstract hyperplanes, okay, to separate data. So you could have a data here, another data here, another data here. Okay, so this kind of combinations happens as you go further in the layers, okay? Here's another example. You have the data, it's not linearly separable. So the first layer draws straight lines, and then a second layer combines these lines and forms this region that separates data. Okay.
Hi.
Well, but let's start putting this in some mathematical formulation, okay? So,
Hi. Yeah. I'm a little bit confused yet about the nature of what you're calling hyperplanes now. Before they were indeed, I think, hyperplanes in the sense of spaces of dimension 1 less than the space of the multi-dimensional space you were considering, but now I am unsure about what you're producing. Is it like all the... You have a series of hyperplanes.
yeah.
They are considered integrally, or parts of them are considered, and the region that the limit is also considered. So
Yeah, it's the region. Yeah, you have straight lines, for example, but remember, I'm just giving an example of 2 dimensions. Okay? So I draw straight lines, and then the next layers combine these straight lines and constructs this surface. I mean, you can imagine as a surface that separates data. Okay? It's a combination of hyperplanes. Let's think about that. It's a combination of different hyperplanes, in this case are lines, that separate data. Okay? But you can extrapolate this for like a multi-dimensional space. Then you are going to have something there that it's separating the data. Okay? You can think about, for example, think about images again. Okay? You have the space of all possible objects. Okay? So you have some neurons that detect what are specificities of this kind of object here. You have another neurons that detect other specificities of another kinds of objects here. Okay? And with this with these specific neurons that detect specificities like corners, colors, etc. At the end, you combine all of these and you can detect objects with specific colors, specific formats. Okay, it's more. But think about in the easiest way, separating data is exactly what you said. Okay, each neuron draws a hyperplane, and the next neurons will combine these hyperplanes. Will combine and form abstract formats. Okay, combine straight lines and start to separate things. Nice. Okay. Any questions? Any more questions? So let's start to put this in some mathematical formulation, okay? So let's consider a multi-layer perceptron. What we have here is a training instance. Okay, it has its features and a desired output, okay? So, and this is the signal produced in the output of this neuron, neuron J, okay? That is in the output layer. Yeah, and it is the output corresponding to the instance X that was applied to the input layer. Okay? Now, so with this we can compute an error signal. Okay? The error is going to be the desired output minus the output of the neural network. Okay? It's not just a neuron now. Okay? It's a whole neural network. Okay, so it's the output for one instance. Okay, having the output of one instance, what we can do is to calculate the instantaneous error for one neuron. Okay, now suppose that our neural network has, I don't know, N10, for example, 10 neurons in the output layer. Okay, I can have, for example, a classification problem where I have 10 classes. Imagine a problem with 10 classes. Okay, so I can have 10 output neurons in the output layer of my neural network, each output neuron associated with a class. Okay, so I can compute an error for each neuron. So here I am calculating the instantaneous error for one neuron. The neuron J. Okay? But if I have many neurons in the output layer, I can calculate the total error of the network, just summing the errors for each neuron. Okay, so C here is a set of output neurons. I'm just summing up the errors for each neuron. I'm calculating the error here as desired output minus predicted output squared, okay? That's why the E here is squared. Okay, so I'm calculating for all neurons. Okay, but if we have n examples in our training data set, the average error over all examples, that's what we call here the empiric risk, is going to be given by this. Okay, I'm going to, for each instance, I'm going to calculate its error in all neurons. And I'm going to do this summation for all instances. Okay, and make an average here. Nice, these two just went here. I'm going to perform an average here. Okay, so this is, look, it's an average of the error that was obtained by the neural network in each instance. See? Good. And just go back just a little bit. Remember that for the perceptron, we calculated the derivative of the error in the direction of the weight vector. We are going to do the same thing here. We're going to calculate the derivative of this error, the error of the whole neural network, okay? We're going to calculate the derivative of this error in the direction of each weight of the neural network. Think of putting the weights of the neural network. Let's suppose the network has 10,000 weights. You are going to have a vector of 10,000 positions. Okay, each position is going to be a weight. Okay, and then you are going to calculate the derivative of the error in the direction of each of these weights. Okay, this is the gradient vector. And then we are going to calculate, okay, using the gradient descent algorithm, we are going to do, doing this derivative, okay, for every position, okay, we are going to go in the opposite direction, going to the minimum of the gradient, and then go to the minimum of the function. That's the idea. Okay, so if during many interactions you perform this derivative of the wages in the derivative of the error in the direction of each wage, during many interactions, you are going to get to the minimum of the error function. Okay, but now you don't have a guarantee like before. Okay, there is a theorem that says that a neural network can classify, can approximate any function if provided, for example, with 2 hidden neurons and 2 hidden layers and a significantly number of hidden neurons. But it doesn't, the theorem doesn't say anything about training time and number of neurons. So it considers that you can have an infinite number of neurons. But of course, you can never have an infinite number of neurons. So, okay? So what we do is to train the neural network until a minimum error, an acceptable error. Okay, we are not going to, how can I say, we're not going to predict correctly all the classes, okay? Nice, but we are going to have a neural network that has an acceptable error. And it's going to be a very good neural network in predicting new instances, okay, with a very small error. Is it okay? So, before lunch, let me just... A coffee break, yeah, we are not in the morning, but okay. Yeah, I was giving classes only, yeah. The last class started 11:30, yeah. So before coffee break, okay, this is just a drawing, a formulation of a neuron, okay? So we have a neuron J here. You see we have a bias associated to input, okay? And look at now here. The inputs of the neuron, okay, can be input signals related to instances, or as here, outputs of previous neural network, previous neuron, sorry. Okay? So the inputs of this neuron J here are the outputs here of other neurons. So that means that for every layer I have a bias. Okay? Now getting the output, the linear output of the neuron, just one neuron of a layer, I give this linear combination to a nonlinear function. We are going to see some nonlinear functions. And then we calculate the error of the neuron, okay, performing the desired output minus the output of the neuron. Good? Okay, so I'm just putting here, see, in a mathematical formulation. You already saw this, right? So we call this, okay, the activation potential of the neuron that's produced using the input associated to a given activation function. So here, n is the number of inputs, okay, excluding the bias. And Wj0 is the weight applied to a fixed input plus 1, that's the bias. Here. And we are going to see this so before the coffee break. So we are going to get a signal, that's the output of the neuron. The output of the neuron will be the resulting of applying a nonlinear activation function to the linear combination of the neuron, and then we are going to perform, okay, a correction in the weights. And to obtain the correction in the weights, we have to perform this derivation, as I told you, okay? We are going to calculate the derivative of the error surface in the direction of every weight of the neural network. Okay, so with this, we are going to adjust the wages, but I'm going to tell you later. Okay.
Okay.
Question?
Not really a question. I'd like to ask for us to like continue after the coffee break because it was supposed to start like 10 minutes ago.
Okay.
It's
Let's.
at 15 to 11, and I think it's going to be more productive after we have coffee.
No problem. Yeah, just stop it here. It's a good moment to stop.
Thanks.
And how 15 minutes? How long is the coffee break?
No, it's
11:30. Okay.